We have the monotonic convergence theorem, which if you take like 2 seconds to think about what it says, it's very obvious. Very, very obvious.
I love how we say that because we already know it, but there's so many people listening. They're
No,
like, yo,
no.
this is just not obvious.
No, but if you just take 2 seconds,
Okay,
you'll
explain
be
it.
like,
Let's see.
here it is.
Let's see the let's
Okay.
hear it.
So if your sequence is monotonic and bounded, then it converges. Okay? So let's just take 2 seconds here to think about it. So bounded inherently means, bounded above and below, meaning that there are definitely two values within which your sequence stays. Okay? Second thing, it's monotonic. Or actually, sorry, in the monotonic convergence theorem, it says your sequence has to be eventually monotonic. This just means that there is a point at which, every single number past that point is strictly decreasing, strictly increasing, or non-increasing or non-decreasing. Okay? But remember, you still have that bounded property, which means that it doesn't really matter what happens before that point where it's monotonic, because you still know that it's bounded.
Yeah.
But, boom, it's either strictly increasing, but it's still bounded, which means that, it kind of looks like one of those 1 over x situations where, every value keeps going down, getting closer and closer to that lower bound or upper bound. It could be flipped, but it has to continue to decrease because it's monotonic, but you also know that it's bounded, which means that it gets closer and closer to one value, meaning that it converges. Boom. Monotonic convergence theorem.
C.
Very useful. Oh, very useful.
Very useful. Yeah. Very useful. Another kind of consequence of that is, well, the other way around, right? If it's monotonic and non-bounded, like if it's not bounded above. So for example, let's say it's monotonic. So like, let's say it's eventually increasing and it's not bounded above, or it's eventually decreasing and it's not bounded below. In both of those scenarios, this limit will go to infinity, right? So it basically diverges, right? Because there's no bound. So again, I totally understand what you mean once you explain it, because again, it's very obvious once you're just like, oh yeah, well, it doesn't have a bound on the top and it's always increasing. So obviously it's going to go to infinity, right? So that could be like an obvious thing of the MTC, right? Which is a very popular, it's basically like a way to test for convergence, right? A lot of what we do in sequences and series is ways to test said sequence, said series. And I think in series is really where they're all the crazy tests, right? All those crazy tests are in the series, and we're going to get to that. But again, what will this allow us to do? This will allow us again to basically to conclude if this thing converges or not. And if it converges, big advantages, very, very big advantages. Let me explain. So properties of converging sequences are, well, almost, I think, they are almost identical to that of just variables. So like limit as the sequence goes to infinity of a plus b, where a and b are two sequences. You can just take them separately. You can add the limit separately if they're converging.
They're linear.
They're linear. There's the multiplication rule. There are all of these rules that apply if they are convergent. So again, the point of all of this is basically to test for convergence. And then once we have that, we can make a conclusion based on another sequence or adding another sequence and stuff like that, right? So there are a lot of advantages. And again, because of the relationship between sequences and all these things, you can even apply rules that apply to functions on sequences, like the squeeze theorem, for example, right? So just like different things, again, just applying onto these, right? Exactly. So if you have something to say?
I think what you said a little bit earlier was for series.
Oh, did I mess up again?
When you say you can add them together, because if you have two sequences, you can always add two sequences together. It doesn't have to be convergent or anything, right? But if you want to add two series together, then they have to be convergent. Or if you want to multiply a series by a constant, then it has to be convergent for it to actually mean anything, right?
So not exactly. Because if they're non-convergent sequences, you can't add them.
Why?
Because what they're adding is not the sequence itself. So the property is with the limit of the sequence. I don't know if I stressed that.
Yeah, you didn't say that.
I didn't say that? Sorry.
No.
This whole property is with the limit of all of these sequences. So the limit of the addition of two so basically again, when I say a limit, I'm basically saying what is that converging number? What is it converging to? So limit of as n approaches infinity of a plus b can be split up into limit as n approaches infinity of a plus limit as n approaches infinity of b, provided a and b are convergent sequences. And this applies for multiplication, this applies for division, power, all of them. So again, it's just a fancy, helpful way to kind of provide these two sequences together, right? So that's why, again, honing in on the importance of convergence is basically where I'm getting, right? That's basically the point of this.